All right, so we're looking again at this accumulation function. We are on number 28, the accumulation function. Accumulation function. It's that capital F that we've been kind of going over, that buildup of area. Now, instead of just simple boxes or a simple triangle, we're going to do a little bit of a combination of boxes and triangles. So let's start out by kind of building this as a metaphor. So I'm gonna look at this as snowfall. That's why we have the snow here. Um, this is a measure of like the rate of snow. So for example, at x equals 1, right here, at x equals 1, the snowfall is 3 inches per hour. And that's what's happening. But if we were to see right here at 0, it was 1 inch per hour, and it's steadily built over the time. You know, it's like the storm's moving in and the snow is building up. So what we have then is this interesting build up. You know, all this here is build up. So all that is positive. But then at time equals 2, we're still building, and then here at time equals 3, something interesting happens. It stops snowing. So then what's this drop here? Well, snow is not permanent. It has to be cold, and it's not freezing all the time, so it sometimes melts. And then we get this negative here. This is a melt. And then this blue here is this, it's building. This is the buildup. And then we got build up again. And then we got more melt again, this red down here. So we need to find these areas and calculate them over time as they grow and then decrease as well. We have this increasing and decreasing. So let's find each of these areas. Now we're going to fill out a table that measures the area numerically as we grow, but I actually think it's very helpful if we split up the area first. For example, here, let's just find the area of these pieces and see what they are. Well, this first one from 0 to 1 here, this is a positive because we are building up. We're above, we're increasing, we're growing. So we have a box here that's worth 1. And then this triangle, it's too tall, 2 units tall by 1 unit wide. So that triangle also has an area of a +1. So altogether that's +2 if we were to look at that section. Now in between 1 and 2 here we have 3 boxes that are each +1, +1, +1 because it's a 1 by 1 box. Now for this triangle, let's kind of keep all that together. We got 3 units high by 1 unit wide, so, and it's 1 times 3 halves or 1.5, and then divide that by 2, or no, 1 times 3 and then divide by 2. So that gives us a positive 1.5. Let's really simple decimal there. So all that's building up, and then at 3 here, now we start to get smaller. So let's find this triangle is 4 units down and 1 unit wide. And the area of that would be, you know, base times height divided by 2. So 1 times 4 divided by 2. So that's, or not a +2. Whoa, what are we thinking? This is minus. So this little triangle here, this is -2. And similarly with the same dimensions, this is also -2 because we're 1 unit wide and 4 units down. Now remember, we're just calculating area, and because these ones in the middle, we're moving to the right, but then we're also going down, and that's a negative and a positive, and the product of those two numbers is going to be negative. Now for these other ones over here, we were moving to the right and then up to calculate that area, so that's 2 positives. Now we're just moving to the right every time for this example, but in future ones in this video, there's going to be somewhere I move left, and that might change. So, you know, that's not a universal happens that way every time, but for now, it's kind of consistent. All right, for this next one, we are building up back again. We are 1 unit tall, 1 unit wide, and we're going to split that in 2 because it's a triangle. So this is a +0.5. Now this blue triangle here is still building up, but it's smaller yet. It's only half a unit wide by 1 unit tall. So it's a half times 1 and then divided by 1, divided by 2 again because it's a triangle. That's only plus 0.25. Okay, let's look at this triangle and box on the last one. So again, we have the same dimensions for the triangle, except it's negative because we moved to the right and then down. So that's going to be a negative 0.25. And then this last box is just a 1 by 1 box, so it's just negative 1. All right, so we got kind of our measurements all roughed out here. Let's use them to accumulate and see what we get. So in the first one, when we start at 0, we have no area. We go from 0 to 0. There's no width, so that's just 0. Easy enough. But now as we move to t equals 1, or x equals 1, I should say, the integral from 0 to 1, that's the area between 0 and 1. And we found that to be that box and the triangle sitting on top of it. So we got to add 2, and that's going to give us 2 so far. Now if we're doing the integral from 0 to 2, we're going to use the work that we've already done from 0 to 1 to help us with that, because that's the integral from 0 to 1 plus the integral from 1 to 2. So all we got to do is take the area we already had, which was 2, and add the new area between 1 and 2, which is going to be 3. So we add 3, and that gives us 5. Now we're going to repeat that process. So between 2 and 3, how much area is added? That would be here. We're adding another 1.5, so we're going to plus 1.5. And that's going to give us 6.5. All right, now is when we start to subtract. Let's change color, just something a little bit different, just to show exactly where things change. Let's do like a gray. Now we're going to subtract 2, because that's this area down here. So we subtract 2, and now we're at 4.5. And then we subtract 2 again because it's melting away. So we subtract 2 again, and now we're at 2.5. And then now that we pass from 5 to 6, we're back in the positive. So now here we are. We're moving from 5 to 6. We're going to add some area. How much area do we add? Well, that little triangle sitting on top is just a 0.5. So plus 0.5. And that gives us 3. And then when we move from 6 to 6.5, here right in the middle, we add still yet another quarter, 0.25. So that gives us 3.25. And what else do we got? The 7, when we move from 6.5 to 7, now we subtract it. So let's change our color again, back to gray. So subtract that quarter back. So now we're at 3.0, I guess you could say. And then we are subtracting again this last final box of -1. So we're going to subtract 1, and we finish at 2. Now you might be thinking, but you just did that step by step. Could I do it all kind of like just find one of them without going through each one individually? Yeah, you can. So for example, if I wanted to find the area from 0 to 5, I would take all the positives, all the negatives, add them up, and see what I get. And from 0 to 5, I got, let's see, 6.5 positives. And then for the negatives, I got 4, and that would give me 2.5, which is the same thing that we got. But we were just doing it one step at a time. So you don't have to do it one step at a time. You can jump right to any number and just kind of total up the positives and negatives within those boundaries. So in this case, between 0 and 5. All right, so now we got some numbers, we got some data. Let's start going deeper. Let's look not just at f, but also f prime. And this is where it gets so interesting. because I don't know if you see this, but I see right here it's telling me take the derivative. But that's exactly what that means. But right here, this dotted part that I'm underlining, that's the I'm supposed to take the antiderivative. So in other words, what it would be telling me to do in like a verbal prompt, it would say take the derivative of the antiderivative. What? So it's like I start with a function, I take its antiderivative to figure out what that is, but then I take the derivative of that and I get back to where I started. So in other words, I'm expecting to happen that the derivative, d dx, and the antiderivative cancel each other out. So the d dx and the antiderivative are probably going to cancel each other out. So in other words, what happens if those two pieces disappear? If that is just gone, then that means this would be the same thing as f of t, or really, in our case, we could say f of x, or f of whatever. That's kind of what we're expecting to happen. So now we're not looking at area, we're just looking at the vertical coordinate, like what we would consider like a y coordinate. So when x equals 0, what is the vertical coordinate? In other words, what's f of 0? Well, it's not 0. And people want to say it's 0, but what is that coordinate? Let's start coloring these in. How about in this brown color? That's 1. So f of 0 is 1. F of 1 is 3. F of 2 is 3. F of 3 is 0. F of 4 is negative 4. F of, I should be saying little f of 1. And this is little f of 2 and little f of 3 and so on. So what's little f of 5? That's 0. And what's little f of 6? That's 1. 6.5 back to 0. 7, we are down to negative 1, and then we stay there for 8. Okay, so we got that information so far. Let's kind of see how that's working for us. So I'm going to erase some of these numbers. I'm afraid to use my eraser because it's been freezing on me lately. So I'm going to go really slow with it. Alright, there we go. I want to add some interpretation here. We just did a derivative, and when we do a derivative, we're really interested in those positive and negative values. So we got positive, 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 0, and then we're down to negative, and then we're 0, and then positive, and 0, and negative, negative. So that's going to help us as we look at the upcoming prompts here. So let's do that. Let's look at them. Let's interpret. On what subintervals is f increasing? All right, so let's think about this. F increasing, when we say capital F is increasing, that means that capital F prime is greater than 0, which also means that little f is greater than 0. So all we're looking for is above the y-axis, or above the horizontal axis. So when does that happen? If we were to look back at our function here, when are we above? Well, between 0 and 3. We are above the x-axis, all that blue area. I did this on purpose, by the way. I am color coding this. This is from 0 to 3. And then it also happens again, and from 5 to 6.5. It happens there as well. So on the other end, f decreasing means that capital F prime is greater than 0, which also means that little f is greater than 0. So now we're looking for below the x-axis. It's all the other values that were negative underneath that horizontal axis. So that happens between 3 and 5. And where else? Between 6.5 and 8. All right. Where in the interval, now we're on D, where in the interval does f achieve a minimum and a maximum? Now there's something implied here. When it says when does it reach its minimum or its maximum, they're talking about absolutes, not just any min or max, but the max and the min. Well, a couple things we need to check. First, we got to check our endpoints. And those endpoints in question are 0 and 8. So we got to figure out what's f of 0 and what's f of 8. Well, we did that already. But then we want to check local extrema and see if those kind of give us a min or max value. And remember that a minimum happens when we change from decreasing to increasing, and vice versa. A maximum changes from increasing to, oh, I said this backwards. Minimum was decreasing to increasing, so maximum is increasing to decreasing. So when does that happen? Well, when do we change from the blue to the red? That would be our max. That happens at f of 3. So that's a potential maximum, but we have to check it against the endpoints. And the minimum would be when it changes from the red to the blue, which happens at 5. So what's f of 5? So we got to check all 4 of these values, see what they are. It looks like f of 0 is 0. We figured that out. F of 8 was 2. F of 3 was 6.5. And f of 5 was 2.5, I believe. But let's double check those numbers just to make sure. So f of 3, not f prime, but f of 3 and f of 5. We got 6.5 and 2.5. So both of those were correct. So what is the min and what is the max? Well, let's see. The biggest number out of all these right here is f of 3. So this is our max. It's at 3 and the value is 6.5. So we're answering both questions, both parts of the question there. And where's the min? It's here at 0 and the value is 0. All right, so that wasn't too bad. So now we got to find the concavity of f. Concavity of f, that's kind of crazy because concavity of f means that we're trying to look at f double prime. But we know that f prime, capital F prime, is the same as little f. So then that means that f double prime, capital F double prime, is really the same as little f prime. And how can we use our picture to really look at little f prime? Well, little f prime is the derivative of the picture given, which means this is the slopes. So the slopes of the picture that we have, not the area, but just the line, tell us about the concavity of f. So we're looking for this capital F. So the slopes of little f tell us about the concavity of capital F. So when are those slopes positive? When are they negative? Well, let's look back at the original picture. Looks like we got here a positive concavity, then a 0 concavity, then a negative concavity, and pardon me, we have a negative concavity still here because this is negative slope, and we got a positive concavity here, and still positive concavity because the slope is positive. Then we're negative all the way through there, and this is a 0. Okay, so how do we know there's a point of inflection, or we're measuring concavity? A point of inflection, or an inflection point, however you want to say it, happens when f double prime changes sign. Not just goes to 0, but it has to change sign. Otherwise, we can have a section of the graph where concavity is kind of empty and it's positive before and negative after, but to have a point of inflection, an individual point, we have to change sign. And that only happens at one place where we switch from positive to negative or vice versa. And it's right here. So that is our point of inflection. So now we get to the point where we can sketch a rough draft of this picture. Let's start that rough draft sketch just by plotting some points. Okay, so we're plotting points. F of 0 we know is 0. F of 1, oh, by the way, is there anything different about this? No, let's go ahead and graph it. F of 1 is at 2. And then after that, we're 3 higher than that. So at F of 2, we're at 1, 2, 3. Oops, not high enough. Up here. And then at 4, we still went up even more, all the way up to 6.5, kind of right in the middle. And then, so we're at 4 now. And then at 5, this is where we started going down. We subtracted 2. So we're going down 1 and then 2. We're at, what's that, 4.5. And then at time equals 6, or at x equals 6, now we subtracted 2 again. So we're all the way here at 2.5. And then now we're at 7. Once you're at x equals 7. Oh, did I skip a number? I totally skipped a number. 1, 2, 3. I better erase some of these numbers. Got to be careful with this eraser. Alright, let's fix. Let's see what we got. So we're here at 3. And then we did, these numbers are still correct so far. Let's see, where are we at 6? What is f of 6? Well, I know f of 8, based on the information right above me, is 2. And f of 7 was 1 above that. But what's f of 6? Well, f of 6, we added a half. And then f of 6.5, we added just a little bit more than that, just a little bit more than that, just like that. Okay, so that's kind of the picture that I see so far. So let's talk about increasing, decreasing. We know we're increasing from 0 to 3. So that's true. And what's our concavity, though? So let's make a kind of a concavity interval here. So when we're talking about concavity, f double prime versus x, when do we change concavity? Well, from 0 to 1, we were concave up, but then it was 0 from 1 to 2, and then from 2 to 3, actually from 2 to 4, we were concave down. And then from, let's see, 4 to 6.5, we had concave up back on that other screen. And then from 6.5 to 7, is it from 6.5 to 7? No, it's from 6. This is from 4 to 6.0. It was concave up. And then from 6 to 7, we're concave down. And so actually that means that we have a point of inflection here as well. We missed that one. Then from 7 to 8, we are back at 0. So it's kind of like there's no bend in the line. When you have 0 concavity, there's no bend. It's just a constant slope. All right, so from 0 to 1, we are concave up, which means we're going to look like this. But then from 1 to 2, it's just flat, nothing in it. Then from 2 to 4, we have a concave down, and that makes sense with the way these curves are going. And then from 4 to 6, we are concave up again. But then from 6 to 7, concave down again. And then from 7 to 8, flat. Not flat, I should say, straight. No curve, no bend. All right, so there is our rough sketch. All that work just for that little sketch. So we're going to go even further with this in the next part of this video. But this was a big part of this video. Rewatch this video if you need to. I'm going to make a part 3. This is huge. This stuff is big. So watch it again. Pay attention to the color coding too. It's very, very particular on the color coding. All right. See you in part 3.